Now let's consider another example where the off-diagonal terms are going to show up. Let's consider again a unit mass, but now that it's in a position 1, 1, and 0. So not completely located in one of the axes. So again, let us understand how the torques will operate. So the arm has a component in X and a component in Y. So force in X will pick the Y component of the arm and produce a torque in Z. Now, likewise, if you have a force in Y, this force is going to pick the X component of the arm and also produce a torque in Z. A force in Z, however, will be picked by both arms and will produce torques in both X and Y. That is to say that if you torque the X direction, you will also produce a rotation in Y, and vice versa. If you have this body and then you start rotating it around the X-axis, inevitably, you're also going to produce a rotation around the Y-axis. That is to say, this force here, if you accelerate this body in the Z direction, you're going to end up producing rotations both in X and Y. So let us see how the tensor formalism describes this situation. Again, we have that the positions are 1, 1, and 0. So let's get back to the inertia tensor, which is given by this expression, and put here x equal 1, y equal 1, and z equals 0. These are the inertia moments that you get. So in matrix form, you have this inertia tensor and the relations between the torques and the angular accelerations. Write this then in components for the three equations. This is what we get. Tau x is equal to alpha x minus alpha y, tau y is equal to minus alpha x plus alpha y, and tau z is equal to 2 alpha z. So what is the interpretation? Indeed, we see that a torque in Z only produces a rotation around the Z-axis. That's what we see here in these two examples, the force in X and the force in Y. They both produce a torque in Z. And this torque in Z, they only produce a pure torque in Z, so you only have rotation around the Z-axis. However, a torque in X will not be restricted to the X direction. It will produce rotation around both the X axis and the Y-axis. Notice also that the signs are different. The signs are opposite. If this torque leads to a counterclockwise rotation in X, it's going to lead to a clockwise rotation around Y. And this is indeed what we see here. You have a force in the Z direction. You have a torque in the X direction. And this rotation in the X will also be accompanied by a counter rotation in the Y direction. And likewise, a torque in the Y direction will not be restricted to the Y direction either. It will also be followed by an angular acceleration, a rotation around the X axis, and again of opposite direction. That's what is happening here. If you have a torque in the Y direction, you will also produce a torque in the X direction of opposite sign. So this is precisely what we intuitively concluded from examining the forces with the right-hand rule. The tensor formalism reaches the same conclusion with rigor and in a more direct way.